Last week, we introduced the master plan of the Minato Mirai project as a TOD-based high-density mixed-use development. It required a vertical and horizontal circulation-focused design, which became the urban core. Now, I'd like to talk about the construction challenges in realizing the urban core of the Minato Mirai district and how those challenges were resolved. The development of high-density mixed-use buildings and efficient transit system is a fundamental aspect of TOD, transit-oriented development. In TOD systems, a vertical circulation-focused space connecting the station and the building above is called a station core, and Minato Mirai Station is a prime example of this. Furthermore, when horizontal circulation is integrated, the space is referred to as an urban core. Our site serves as this kind of urban core. So what are the conditions for a space to function as an urban core? An urban core combines high-density mixed-use buildings with transit systems, and to efficiently manage the increased pedestrian flow, alignment of pedestrian pathway is essential. Realizing an urban core involves numerous engineering challenges. Let's take a closer look at what those challenges were. During the construction of Minato Mirai Station, Queen's Care was already in operation. Minimizing construction time and ensuring safe execution were critical priorities. At the time, they had to avoid disturbing the foundations of existing buildings while solving the problem of soft ground, requiring advanced construction techniques to build new underground structures. To avoid disturbing the foundation of existing building, the underpinning method was used, reinforcing the base incrementally from beneath. To address the soft ground issue, the pre-loading method was applied. By applying load in advance before construction, ground consolidation and settlement were induced early, preventing future subsidence. Using the pre-loading method, the soft ground was settled in advance, securing overall ground stability. After the pre-load process, steel pipe parts were driven deep into the ground to create a structural foundation for the new building. To avoid disturbing the existing foundation while reinforcing the soft ground, the deep mixing method was applied, injecting cementitious materials deep into the soil to solidify and stabilize the foundation. Large vertical shafts were drilled into the ground and the concrete foundations were extended. Then, using TBM and NATM methods, tunnel spaces for survey operation were excavated and secured. With existing buildings in operation and a dense concentration of surrounding structures, these complex construction methods were applied in precise coordination. Another major challenge was the existing 7-km common duct beneath the building. The utility tunnel or common duct is an underground conduit carrying essential infrastructure, electricity, water, telecom, and HVAC systems, making it a crucial and highly sensitive part of the urban network. Building the station both above and below this tunnel posed a major construction challenge. To solve this issue, the common duct was temporarily supported with steel trusses and secured with pipe frame, and excavation proceeded from below and from the side. Another challenge was the vibration caused by moving trains underground. This vibration could interfere with business operations above or even damage the structure, making it a critical issue to address. Controlling the vibration caused by trains was crucial, and to minimize contact with the base floor, a cold spring floating slab system was implemented. This technique, which suspends the rail carrying slab using springs and rubber, effectively absorbs low frequency vibrations under 10 Hz, while also providing sound insulation benefits. Minato Mirai Station lies 5 levels underground, while the main pedestrian flow occurs on the second floor above ground. To seamlessly bridge these 7 levels, a spacious and open vertical void was essential. While the expansive void space created a powerful visual impression, it posed serious structural engineering challenges. The greatest issue was how to maintain the space without vertical supports while effectively distributing the loads. The upper levels of the building house high-rise commercial facilities, continuously bearing the heavy loads of concrete structures, dense foot traffic, and mechanical equipment. In a buoy structure where no intermediate columns could be placed, the load had to be transferred solely through the sidewalls and arches. This resulted in significant bending moments and axial forces. Another critical issue was vibration transmission. In wide spaces, vibrations propagate more easily, and with high pedestrian traffic, the structural behavior near its resonance frequency. Since this was an active platform with constant movement, dynamic loading had to be carefully addressed. To solve these structural issues, a semicircular reinforced concrete arch was adopted. The arch distributes vertical loads laterally, reducing bending moments and providing external resistance to vibration. The semicircular reinforced concrete arch is considered the most ideal form, converting vertical loads into horizontal compression forces distributed to both walls, allowing for a wide column-free space. To construct a semicircular RC arch with precise curvature, accurate formwork known as centering was essential, since installing a 70-meter long centering frame at once was impractical. It was assembled in segments and was considered for stage construction. This method allowed for safe construction even in confined space. It also offers advantages such as the reusability of centering and the prevention of deflecting during concrete curing. To shorten the construction period, off-site construction techniques were adopted. Rebars were prefabricated in the factory and assembled on site using a prefabricated rebar system. This approach enabled uniform quality and a shortened construction timeline, while also allowing high precision work to accurately preserve the curvature of the arch. Minato Mirai Station has a total of 8 entrances, each directly connected to surrounding facilities and seamlessly integrated into the pedestrian circulation network. From a circulation engineering perspective, the most critical element was the horizontal connectivity and centered around Level 2. This level served as the primary pedestrian axis linking the station to surrounding facilities. During the design phase, a key objective was to create Level 2 as a dedicated pedestrian expressway, separate from ground and underground level. Artificial decks were used to establish a continuous circulation spine across the city. Level 2 was designed as a continuous pedestrian link from Sakuragucho Station through Queen Square and Landmark Tower to Pacifico Yokohama. More than just a connection, it strategically avoided existing mechanical loops and vehicle paths, forming a high-speed pedestrian spine across the urban fabric. To realize Level 2, engineering solutions addressing both vertical and horizontal pedestrian axes were required. To connect the station on basement Level 5 to Level 2, a large vertical void and a grand escalator were introduced. This atrium structure not only provided visual openness, but also secured intuitive connectivity throughout the space. To realize horizontal connectivity at Level 2, overcoming the elevation differences between buildings was a key challenge. Inclined bridges and lightweight steel structures were introduced, minimizing level gaps and allowing for a smooth natural pedestrian flow. The pedestrian circulation at Minato Mirai Station was designed based on circulation simulation across the urban core, centered on 3 primary axes: the Queen axis, King axis, and Grand Mall axis. The most efficient central path was first identified. 8 entrances were then strategically positioned to avoid existing structures and align with key urban functions. Serving as the urban core within the Minato Mirai district, the Yokohama Landmark Tower and Minato Mirai Station faced multiple challenges during construction, including existing structures, utility tunnels, vibration control, large void spaces, and complex circulation paths. Through precise engineering solutions, these issues were resolved, leading to the creation of a seamlessly integrated urban system. Now let us walk you through our study plan.